Okay. So now we will continue this chapter. Let me focus on the screen. So now we will continue chapter 1. So again, chapter 1 we have 7 points. So far we are in point number 4. Hopefully we can finish this point today and we'll start point number 5. What we have remaining in point number 4 is to explain what is the difference between steady state and equilibrium. Did anyone hear about steady state before? You heard this word before, right? Does anyone know or can explain what is meant by steady state?
Means that even though things are going in and out, it stays at the same level. So it is poorly described, but
In and out at the same level, right?
yeah.
Any other description? Any other thoughts?
Isn't it that there's no change due to time?
There is no change to atom. Okay, let me put you something. So let's say I have two systems here. Let's say I have these two pipes. And I ask you, can you just tell me which one of them is a steady state or no? So let's assume we have two technicians. One of them, let's assume we're measuring temperature, for example. So we're using thermocouple. So one bring thermocouple, put thermocouple here at this position, and start to monitor how the temperature at this position will change with respect to time. So this is what the first technician did. Let's say another technician, he said, okay, instead of this, I will use two thermocouples. So I will use thermocouple here at this position and measure temperature at this position. Let's call it T1. And we have another position, let's say at the outlet, for example, and at the outlet, I will put another thermocouple, I will measure T2. And they recorded their observations. So let's say the first one here, he said, okay, when the time is 1 p.m., let's say 2 p.m., 3 p.m., he collected measurements at this time interval. At 1 p.m., so the temperature, let's say it's 15 degrees Celsius, 20 degrees Celsius, 30 degrees Celsius. Here, let's say at T1 was 20 degrees Celsius, T2 is 30 degrees Celsius. So let's say this is case number 1 of the measurement. This is case number 2. Let's make it more general. We have 4 cases. So another one, he said, that is case number 3. This is related to this one. So case number 3, when time is 1 p.m., 2 p.m., 3 p.m., the temperature is, let's say, 20, 20, 20, and case number 4, can you see it? Okay. Let's say T1 is 25 degrees Celsius, T2 is 25 degrees Celsius. Okay. So let's see, we have these 4 cases. Okay. So one said I will use only one thermocouple, fix it at one position, and see how the temperature will change with time. And he recorded the measurements of temperature with respect to time. So one time, when time change, the temperature will change. This was like case number 1. Another case, when time change, temperature will be the same. Or we will use 2 thermocouples and we see what will be the temperature just at any time. Like at 1 p.m., for example, I will get the temperature measurement at these 2 positions. So one case, the temperature are different. One case, they have the same temperature. Which case can you describe it as a steady state? 3 and 4. Okay, so I have, okay, the red ones. Let's see. Anyone agree? Anyone disagree? Who agree with this? 3 and 4. Okay, so if you disagree, what will be your opinion? Who have no idea? Okay, so let's say either you don't have an idea or you are okay with 3 and 4. Okay. The trick here, only one case is a steady state. Just one of the 4 cases is a steady state. So let's start seeing 1 and 2 are not steady state. Okay, because basically here we have temperature change, right? Here also we have temperature change, so it doesn't make sense that any of these two cases will be steady state. So now the confusion is 3 and 4, which one of them can be described as a steady state? So let's see the description of a steady state. Steady state process is called steady state when the properties, all properties, here we only focus on the temperature just to make it easy, when properties of the system are constant with respect to what? Time. So this is the key here. We are considering how the properties will change with time, not with position. What I did here in case number 4, I was checking what's happening in the temperature with respect to position, from one position to another position at constant time, from one location to another location. So here in case number 4, I was comparing what is happening with respect to position. But in the definition of a steady state, I was seeing what is happening to the property, how the property will change with respect to what? With respect to time. So this is the only thing here. I see how the temperature will change with respect to time. So this is the case that can be described as steady state, because there's just one word in the definition here. So this is why if you want to describe the process to be steady state, you can use this diagram, for example. Put your variable as the y-axis. Your variable can be temperature, pressure, velocity, mass flow rate, volumetric fluid, whatever property that you need to measure. But the x-axis must be time. And then you start to plot this, the value of this variable with respect to time. If the variable is constant with respect to time, like this one here, so here we have the variable is almost constant, so this time range we can describe within this time range, our process is at steady state. Here we have the variable is constant with time, so here we have a steady state. But at some conditions, similar to this one, for example, we have variation happening in the variable. The value of the variable is not constant. So from one time to another time, you have different value, which is we have here in this one, for example. So this one is called the transient or called dynamic or called unsteady state. All of these words get the same meaning. Okay, clear? So this is what is meant by steady state, and this is what you should do in order to know your system is steady state or no. So pick a position, just one position, see what is happening for the value of your property at this position with respect to time. If it's constant, then it's a steady state. If it's not constant, then it's any one of them, transient or dynamic or unsteady state. Clear? Any questions? Clear? Okay. The last thing in the basic concepts we need to discuss is the equilibrium. Equilibrium, this is related to the driving force. So the system is called, it's at equilibrium if there is no driving force to cause any change in your system, in the properties of the system. Okay, so there is nothing pushing the system to change its property. And equilibrium and steady state, it may be confusing. Okay, so so properties are constant in both of them. But again, steady state, you are observing the value of property only with respect to time. Okay, system can be at equilibrium even at different times. So the time concept is not this is not the core of explaining the concept of equilibrium. If you wanna talk about equilibrium, then you should have or focus on the driving force. This is why. Let's say if we focus here in cases 2 and 4, so here in case number 2, we have difference in the temperature between one position to another position. If you have temperature difference, so you have heat will be transferred. You have transport phenomena or not yet? You don't have it? If you put a cup of coffee, for example, hot cup of coffee in the table, and you leave it for some time, so what will happen to this cup of coffee? To its temperature? It decreases. Why? Because it's surrounded by cold air, right? So we have temperature difference. The coffee itself is hot, the air is cold. So as long as you have temperature difference, so you have heat transfer will happen, which is the case here. Okay. If you have concentration difference, mass transfer will occur. Almost any substance will move from high mass concentration to low concentration. And this is called the driving force. So we have some driving forces, temperature difference, concentration difference. this is why you have transport phenomena course, in which you will study mass transfer, you will study heat transfer, and so on. So if you don't have this type of driving force, this difference in temperature, this difference in concentration, so you will not have any heat transfer happening, you will not have any mass transfer happening, and then your system will be at equilibrium. Is this concept clear? Any questions? Questions? Clear? Okay. So, again, what is happening? The system, if your system is at equilibrium, this doesn't mean that the system is like fixed, okay, or stationary. You have some changes happen, but the effects or the changes happening are canceling each other. So let's say, for example, if we have, let me do this. So let's take water, for example, as an example. So we have H2O at 1 atmosphere. Okay, if you have water at atmospheric pressure, and let's say the temperature is 25 degrees Celsius at room temperature. So this water will exist as solid or liquid or gas. Which phase? Liquid. So this one will be liquid phase. Let's assume I start to increase the temperature. So let's make it 70, for example. So what will be the phase we have? Liquid. Let's make it 99. What will be the phase? Still liquid. Okay. If we have 110 degrees Celsius, what will be the phase? Gas or vapor. Because what is happening here, I have a certain temperature, which is 100 degrees Celsius. At this temperature, what is happening? Phase change. So phase change means at this temperature, I have two phases exist together. I have liquid and I have vapor. Always these two phases would exist together. So if you have water at 1 atmosphere at 100 degrees Celsius, and you look at this system, for example, that has this water, you will have two phases exist. And the amount of liquid, water liquid, will be the same. So what is happening here? Some systems, it says, if you just look at it, you will not observe any change. So let's assume if I have this tank, this closed tank, and here I have liquid, and here I have vapor. So at equilibrium, by your eye, you cannot see any difference. But what we mean of this one, we have cancelling the actions by opposing forces. If have one molecule that was liquid and this molecule evaporates, so at the same time, you will have one molecule from the vapor phase will condense. So this is why you cannot see any change. But this doesn't mean there are no changes happening. Changes are happening. The system is dynamic. But by your eye, you cannot see any change, because if you have one molecule move from the vapor, from the liquid to the vapor phase, at the same time, one mole or one molecule from the vapor will condense and be what? And be liquid. So this is what is mean we have cancelling of any opposing forces. If something push it in the right direction, so this is another thing which is pushing it to the opposite direction. So by your eye, you see there is no change happening. But what is happening exactly that any change happen, there is an opposing change. So the net effect is zero at the end. Is this concept clear? Okay. What are the types or the driving forces that we have to describe equilibrium? We have three driving forces. We have mechanical, it may be thermal, or it may be chemical. And what is the differences between them? Thermal equilibrium, you can describe your system as a thermal equilibrium if the temperature is uniform, it's constant throughout the system. At any point of the system, the temperature is constant. So this is why it's called equilibrium, which is the case like number 4 that we described. If you have the pipe, you put two thermocouples, one at the inlet, one at the outlet. The temperature at the inlet, the temperature at the outlet are the same. So we have uniformity in temperature. So now this system is at equilibrium, because at different positions, temperature is constant. Is it clear? Mechanical equilibrium, so this exists if we have forces or pressures are balanced throughout the systems. All the forces, all the pressures affecting the systems almost are equal. Chemical equilibrium, this one regarding the chemical composition or the concentrations. So this is the driving force for it. And at the end, we have phase equilibrium, similar to what discussed here, if we have two phases exist at the same time together. Okay? So just quick examples, if the system, or what you can see to say your system at thermal equilibrium, so if you have single system, and this system has like same temperature at any position. If you have two systems very close, and these two systems at the same temperature. So the key here is, do you have the same temperature from one position to another position or no? Mechanical equilibrium, this exists if you have like no difference in, as you said, in the forces or pressures between systems surrounding, or if you have systems moving, but this system is not accelerating, so it moves with the same velocity. So this means the whole pressures, the pressure that is forcing it, the pressure that is resisting, these are like canceling their effects. So it moved with the same velocity with no acceleration, or with no deceleration. Chemical equilibrium exists if you don't have any tendency to phase change, if we don't have chemical reactions. If you have any of these, like no phase change, no chemical action, so we can describe our system to be at chemical equilibrium. So this is the last basic concept we have, steady state and terminology. So just a quick summary, we have four concepts that we need always to keep in mind. The first one is system, types of system. Then we have state and properties, how you can classify properties, processes and cycles. And the last one is steady state and equilibrium. Any questions on this part?
Is there a system that can have all types of equilibrium?
Again, so I can't hear.
Is there a system that can have all types of
Yeah.
equilibrium at once?
Yeah, they can exist. Questions? Sure. Can you call him? Questions? Okay. The second part is forms of energy. What are the forms of energy? If you remember that we said thermodynamics, this is the science that deal with what? With energy. So if you want to understand thermodynamics, so we should start with the fundamentals. What are the forms of energy that you will see? So basically, for types of energy, let's start with the types. We have different types of energy. This is why even in engineering we have different disciplines, because we consider all of these different types. We have chemical energy, nuclear energy, thermal energy, chemical, mechanical, electromagnetic energy. We have different types of this energy. The differences between each one of them is the source of where your energy is released. So let's say in chemical energy, for example, energy is coming from breaking the bonds between the substances and forming new bonds. Okay. In nuclear energy, for example, we have the amount of energy released during the fission or fusion. We have the mechanical energy, for example. This is the energy that is happening due to the motion of the position of the objects. So the energy concept is the same, but why we have different types? Because you can get energy from different sources or by different ways. And the concept of energy, similar to thermodynamics, it takes a long time to be the thing that we are understanding or studying right now. So again, it is done by introducing the concept of energy. Then we have Kelvin. He started to use the term energy in thermodynamics, and if you remember, he was the first one that introduced even the thermodynamics term. And then we have, in the last century, we have the potential or the internal energy that is start also to appear. So our rule now is to put all of these types, try to understand each one of them. What is the basic equation that we can use to calculate each one of them? So let's start with the energy we have. We can say any substance, if it has energy, so this means it can produce an effort. It can do something. Okay? Let's say this something can be work. It can rotate a mixer, for example. It can move from one place to another place. So this means this system can energy. It can do something. Or if it will not, let's say, if it will not move, not produce any work, it can heat. You can observe or you can notice this energy in terms of the temperature change. Okay. So again, if any system has energy, so this means this system can do an effort. This effort can be work. This effort can be in terms of heat, temperature changes. Energy is classified into two categories. Energy can be stored in the system, or energy can cross the boundary between the system and surrounding. So if you remember the first thing when we described the system, we said that we have our system and we have boundary, and anything outside the boundary, this is your surrounding. So category number one of the energy, that energy can stay inside the system. Just remain inside the system. Okay? Can it change? Even if they change, they will change the value, but they will be inside the system. And we have types of energy that can move, cross this boundary, so move from the system to the surrounding, or from the surrounding to the system. So these are two categories: energy stored or energy transferred. The energy that are stored inside the system, these are internal energy, kinetic energy, potential energy. So these are the three types of energy that stored inside the system. The energy, or let's start. The internal energy, let's start with comparing them. So internal energy, let's see. Internal energy, this is called microscopic form of energy. Because when we explain it, you see this one is related to the molecules. But kinetic potential energy, this is macroscopic. It focuses on the whole system. You just see the whole system, what is happening to the whole system, make observations on the whole system, then you can calculate internal energy, potential energy, or kinetic energy of the system. But if you need to find the value of the internal energy, then you should look to the molecules of the system. So this is why this is called the microscopic, and the other one is called the macroscopic. And again, since all of these types of energy stored, so they are called static forms of energy. So we have the first one, static forms of energy, energy stored in the system. It can be microscopic, similar to internal energy, or macroscopic, such as internal kinetic or potential. The other one is the energy that can cross the boundary, move from the system to the surrounding, or from the surrounding to the system. We have two types, heat or work. Okay, and this is called dynamic forms of energy, or energy interactions. Okay, so dynamic forms of energy, energy interactions, two terms, but describe the same thing. Describe heat or describe work, because these types of energy can cross the boundary. But in order to understand these types of energy, then we need to start with explaining what is meant by pressure, what is meant by force. Okay, so now we will start just reminding you what is force, what is pressure. Once we understand this, then we can explain each one of these forms what we will have. So if we will start with force, the definition of the force comes from Newton's second law of motion. So this one says the force that affecting is on any body, this is the mass of the body times the acceleration of the movement that this body have. And in order to describe it in different systems, do you remember the system of units? We have the American system, we have SI system, you remember this one? So if we need to describe it, so we have M, this is mass. In the SI system, it's in kilogram. A, acceleration, its length over time square in the SI system is meter per second square. So mass times acceleration, this is kilogram, meter per second square, and all of this is combined together in what is called Newton. So when we say the force is 10 Newton, so it means 10 kilogram meter per second square. In the SI system, mass is pound mass, acceleration is feet per second square, so the force in the American system is pound mass feet per second square. We have one of the famous units that you will see, it's called pound force. 1 pound force is not 1 pound mass feet per second square, but 1 pound force is 32.174 pound mass feet per second square. So sometimes in the problems you will see we have force, the magnitude of this force is 10 pound force, for example. Okay, so 10 pound force, this means we have 32.174 times 10 pound mass feet per second square, and so on. Okay, so just make sure you are familiar with these units. Okay. So this is what I mean by force. Just comes from Newton's second law, it's mass times acceleration, and in SI system we express it in Newton. In the SI system, in the American system, it's pound mat feet per second square or pound force. Then we have pressure. Pressure is force divided by area. So pressure, this is the force acting on any surface divided by the area of this surface. So P, pressure, is force divided by area, and always pressure is normal to the area. So if I have an area here, for example, this is a body or a surface, and I need to find the pressure, so the pressure is applied normal to this area. So this is the pressure we have. So I see what is this force, the magnitude of the force, what is the cross-sectional area, force divided by area. If I have this surface, for example, let's say if I have pipe, for example, and I have fluid moving inside this pipe, so this pipe is my system, so I can see what is the pressure applied to this area, to this cross-section, so the force will be normal to it. What if the force applied to this cross-section, okay, so it will be normal to it. So it's normal and going inward, that it affecting on the system, inward into the system. Okay, clear? What is the units? So we have force in the SI system, you remember, it's in Newton, area is meter square, so we have Newton per meter square, which is equivalent to Pascal. You are familiar with these units, right? You heard it before. So we have Newton, we have Pascal, just to give you an idea about this one. Then we have pound mass feet per second square divided by feet square, it will give you this one. But again, in the American system, we can express pressure as, we have one thing, it's called like PSI. And PSI, this one is equivalent to pound force per inch square. So this is also a very well-known unit we can use to express pressure in the SI system. So now basically, this is what is meant by force, and this is my mean by pressure. Force is mass times acceleration, pressure is force divided by area. How we can use this in order to define the types of energy. So let's start with the dynamic forms of energy. Again, dynamic forms of energy, energy that can move or cross the boundary between system and surrounding. And we have two types, heat and work. If you remember again, we have closed system, energy, only energy can cross the boundary. In open system, energy and mass can cross the boundary. So this is an example of open system, and here this is an example of closed system. In both of them, energy can cross the boundary. And how energy can cross the boundary? Energy can cross the boundary as heat or as work. So here we have heat can added or heat removed. Work done by the system, work done on the system. And similar, the same thing exactly can happen in the open system. If we consider heat, this is the amount of energy that will exist. We will have heat transfer if we have temperature difference exist between the system and boundary. If you have your system, let's take this system here for example. If we have this system at 20 degrees Celsius and we have this surrounding at 20 degrees Celsius, we will not have any heat will move between the system and surrounding. Because what makes heat transfer? If you have temperature difference. So if system and surrounding have the same temperature, no heat transfer. But if your system, for example, is 30 degrees Celsius, so now we have temperature difference, so we'll have heat transfer. And what will be the direction of heat transfer? Heat is always transferred from the high to the low temperature. So the system is 30, surrounding is 20, so the system has higher temperature, so the heat will move from the system to the surrounding. If the opposite, surrounding has higher temperature, so the heat will go toward the system, from the surrounding to the system. Okay? How heat is transferred? How heat will move from the system to the surrounding? So we have three mechanisms. Heat can be transferred by conduction, or by convection, or by radiation, any one of them. However, in thermodynamics, we will not explain them. So this will be completely covered in transport phenomena course. Okay? So here we don't care about the mechanism of this heat transfer. In transport phenomena, this is important. You will go in detail in this one. Okay? But here we only consider with the amount. So at the end, I have this amount of heat added to the system or removed from the system. Okay? And one of the important things, just to note, when you see the problems, or even the description of any problem, I can tell you, here I have heat go from the system to the surrounding, so my system lose energy. Or if the opposite temperature, this is 30, this is 20, so the heat will go from the surrounding to the system. So heat added to the system. This is why sometimes we can see this like sign convention. In the problems, I can tell you that I have Q, the amount of heat transfer is 3 kilojoule. Or the amount of heat transfer is negative 3 kilojoule. So we are using this sign difference just to give you an idea about the direction of heat transfer. If Q is positive, so this means the system is gaining more energy. So this heat is added to the system. If you are making calculations in the problem and at the end you will find Q is negative, so this means your system is losing this energy. So this energy is removed from the system. So the sign here is very important. And even when you read the problem, I tell you that the amount of heat added to the system is 5 kilojoule. Since I said this phrase, added to the system, so you should substitute this number with a positive value, because it's something added to the system. If in the problem I tell you, okay, the system is losing energy of 4 kilojoule, for example. So here I tell you that the system is losing this amount of energy. Why I said it's lose? Because I'm telling you that in the examples, when you substitute Q, you should not substitute 4, but you should substitute what? Negative. Okay, so the sign is very important here. So when you read the problem or when you like find the answers at the end, so make sure that you can describe this sign convention. Positive, this means heat added to the system. Negative, this means the system removes this amount of heat. Okay, clear? So heat transfer happen because we have temperature difference. If we don't have temperature difference, there is no heat. If you have isothermal system, do you remember isothermal system? Isothermal means we have temperature is what? It's constant. Even if the problem, in the problem statement, I tell you, I have like isothermal process, so I'm telling you the temperature is constant, so I'm telling you that Q is equal to what? What?
0.
0. Clear? Any questions? Okay. The second thing is work. Work is the product of the force times distance. If you have an object, if you have a system, if you have a body, you are applying force to this body, to this object, to move it with a certain distance. So F times L times this distance, this will give you the work. So this is why mathematically you express it at this way. So dW, the amount of work that we have in any system equals the magnitude of the force applied times the change in the distance that the system moved, for example. And again, the units, force, this is Newton, distance, this is meter, Newton times meter, this is equivalent to joule. So just remember the difference between Newton, Pascal, joule, you will hear all of these words a lot. Okay? Okay, similar to this one, in the American system, we have one important unit, it's BTU, and BTU is the equivalent to this one. So we have force is in Newton or pound force. Pressure is in Pascal or PSI, and then energy, we have it in joule or PTU. So always keep these units in your mind. So we have this equation for force or for work, but if you remember, we discussed the force before. And what is force? Or force is related to pressure. What is pressure? It's force divided by what? Area. So we have that pressure, this is force divided by area. So if we rewrite this equation, we can say force is pressure times area, right? So if you substitute in this equation, okay, let's start step by step with the slides. So other words, we can express energy as power. This is before the step that I explained. One of the things that we can have work or we can have power. Power is work divided by time. So this is why we have work divided by time. So this, all of this group, this gives you power. So if work is in joule, time this is second, so this is how what start to appear. Okay, so we have F dl by dt. dl by dt, this one is velocity, so this one here dl by dt, this is equivalent to velocity. So this is why we can say the power, this is nothing but the force times the velocity. This dot, if you remember, so this means we have work divided by time. Just any dots, and you see in this course, so this means you have this property divided by time. Okay, so we have work, this is force times distance, or we have power, this is force times the velocity. And again, one of the units that we can use, or you can see in a lot of textbooks, a lot of courses, that to express power is in horsepower. And again, work have sign convention. Also, when you calculate work can be positive or negative, again, based on the direction. So if you have work done on the system, we have the surrounding, adding work to the system or applying work to the system, so it will be positive. So if this work done by the system, so the work will be negative. So any of the two types of the dynamic forms of energy, which is heat and work, we have like an important to consider the sign convention. So we have the sign, it gives you an indication of the direction of heat transfer, indication of the direction of the work that is happening. That this system doing the work on the surrounding, or the surrounding is doing this work on the system. So far is clear? Any questions? Okay. We have three types of work. The first one, we have something called work of expansion or contraction. This one exists if you have system like this one. So you have your system here, and you have a piston. So you are compressing your system. So this is contraction. Or you have expansion. So the volume increase. So if you have any system like this one, any piston like this one, so the type of work associated this one is considered or named work of expansion or work of contraction, based on you are contracting, decreasing the volume of your system, or you are increasing the volume of the system. You have expansion happening. And this is happening in closed systems. So usually you will see this term, or you will see this example if you are dealing with closed systems. So the first types of work of expansion and contraction. So here we have change happening in the boundary, or movement happening to the boundary, and it appears as change in the total volume of your system. And again, this happening in closed system. Okay. And the equation that we are using to calculate the work of expansion contraction is negative integration PDV. So where does this come from? So if you remember, we have work. This is force, or dW. This is FdL. Right? The general equation of work. We said that we have this force can be related to pressure. So we can say force is pressure times area. So we have dW. This one is P A dl. And if you remember from the previous lecture, when we explained the basic units, area times distance, this is equivalent to volume. So we have dW, this is P dV. Just integrate both sides. So here we have work of expansion contraction will be integration of P dV. Clear? There is only one thing missing, which is the negative sign. So why we have negative sign here? Because the relation between pressure and volume is opposite. If you have this piston, if I have this piston and I increase the applied pressure, so what will happen to the volume of the system? Increase or decrease? Decrease, because I'm making contraction. So by increasing the pressure, the volume will what? Will decrease. So PDV, this term or this integration will give a negative value because they have opposite effects. So this is why I add a negative sign here, so the final result will be a positive. Okay, clear? So this is only we have this sign one. And this is how we got the equation. Let's say an example. So here we have a gas. This gas is confined in a piston cylinder device. It has an initial volume of 1 liter. It's heated and expands to volume 2 liters. Okay, so we have heat happening here. So once we have heat, this piston moves up and the volume expands from 1 to 2 liters. Assuming the external pressure is from the atmosphere is 1 bar and the piston has negligible mass, negligible friction, so how much work done by this gas? Okay, so here we have this work, again, it's done by the gas. How we can calculate this one? So based on the equation we have, this is a closed system, we have change in the total volume, so the work we have here, this will be work of expansion contraction. Work of expansion contraction is negative integration of P dV. This is from the initial volume to the final volume. So this one will be negative P V2 minus V1. Just the limits of the integration we have. Put the negative inside, so this will be P V1 minus P2 V2. So what's the units we have? So here the given pressure, this one is 1 bar. V1, this is 1 liter. V2, this is 2 liter. All the units are not consistent. So we need to convert all the units to the SI system. So what is the pressure in the SI system? Nope. No.
PSI.
No.
Oh wait. Pascal.
Pascal. So pressure in the SI system, this is Pascal. The volume in the SI system, so this one is meter cube. So I need to convert bar to Pascal, I need to convert liter to meter cube in each one of them. So this conversion I have, so this one, so the pressure will be 1 times 10 to the power 5 Pascal. So we explained the conversion of units on the first lecture. So if you have this like way, see the units, try to put it, and then you can do it. If anyone has any problem in this part, just let me know. I can do it in detail. I'm assuming that you can do it. Okay, so V1, so this one will be 1 times 10 to the power negative 3 meter cube. And V2, this one is 2 times 10 to the power negative 3 meter cube. Then these numbers I will use to substitute here. So now the work of expansion, contraction, so this one will be pressure, 1, 10 to the power 5, V1, which is 1, minus V2, which is 2, all times 10 to the power negative 3. So if you find this one, this will be negative 10 joule. And this is what I have. How I know my answer is correct? The answer is at the end is negative, right? So negative means this work done on the system or by the system? By the system. And if you return to the example, so the example here, he tells you the work is what? So from this sentence, you can like assume that or predict or even double check your answer. So I have my answer is correct because the answer, the work is negative. So this means this is work done by the system, and this is what is stated in the problem itself. Clear? Okay. So this is the first type of work of expansion contraction, and this happen in closed or open systems? Closed systems. So what if we have open system? If you have open system, you have two other types of work. You have something called shaft work, and you have something called flow work. So now total we have three types of work. Work of expansion contraction, this is for closed systems. We have shaft work, we have flow work, these for open systems. Okay? And again, why this happening? This happen if you have open systems, so you have inlets, so you have outlet, so you have work happening on the system because of the flow. If you have an impeller, any rotating impeller, something mixing or rotating, so this is called shaft work. So in open system, you can have just one of them. You can have shaft work. You may not have flow work. You may have flow work, not shaft work. You may have both of them. But these are the categories that can be exist if you have open system. So for flow work, so again, so this flow work, this is associated with like a flow happening in, you have pipe and you have flow inside this pipe. So this exists because of you have inlets and you have outlets and results from the flow. So this one, we have work done to push the fluids into the pipe and out of this pipe you have. And how we calculate it, it's described as rate, because in open system we have mass flow rate. So it's explained as power. So we have the flow work, this is pressure times volumetric flow rate. And volumetric flow rate, so if you remember we have density, we explained it, it's mass over volume or mass flow rate over volumetric flow rate. So volumetric flow rate itself is mass flow rate divided by density. And 1 over density, this is the specific volume. So we call that 1 over density, this is the specific volume. Specific volume is volume over mass, and density is mass over volume. Clear? So this is why here at the end we can say the flow work, this is the mass flow rate times pressure times the molar volume. Okay? Let's skip the example now. The last one we have is the shaft work. So again, this shaft work exists if you have something rotated in the system. You have a rotating part. You have mixer, similar to the pump, similar to compressor, turbines. Anything has a rotating part. So this one is characterized by rotation, not linear. So the linear movement, this is the flow work, but this one is rotation. Okay, as we said, in pumps, compressors, and so on, if you have no moving part in your system, so it will be 0 at the end. And how we can calculate it? The shaft work is calculated from this equation. Shaft work is integration of volumetric flow rate with the pressure change. With this rotating part causes a pressure change. Is it clear? So 3 forms of, or 3 types of energy, each one of them associated to a system, each one of them has its own characteristics, each one of them has its own equation that you need to calculate. But all of them will give you the same units, because all of them at the end are work. Clear? Work of expansion, contraction, this is for closed, but for open, you have flow work, you can have shaft work. Any questions? So the example that we skipped, we will start it next lecture. Okay? See you next lecture.
Recording stopped.